Hello.
Right.
Hello.
Hi. So for today's session, we're gonna go over chapter 17, 18, the practice worksheet, specifically VF, AM, AW, BP, some chapter 18 reactions that are gonna be other than the Aldol, Michael, and Robinson annihilation reaction, like the soft and hard nucleophiles with the enone, and then some problem set problems if we have time, and practice final problems too. Right. So let's get started on the 17, 18 specific problems. VF, AM, AW, and BP. Okay. V right here. Okay. So for this one right here, whenever you see sodium or potassium, always think of a positive charge. And then that means that whatever is attached to the Na, which is the hydrogen, is a negative charge. This hydride ion minus here is a strong base, right? And then if we have a strong base, we're going to look for the most acidic hydrogen, which is the alcohol hydrogen right there. So we're going to deprotonate that um, alcohol to become this alkoxide ion with the negative charge on the oxygen, right? And that becomes our nucleophile. This is a strong nucleophile, which is able to attack this weak electrophile here, that ketone, right? And when we do that, we're going to do an intramolecular reaction because the nucleophile is on the same molecule as the electrophile. When we do the attack, we have to pop the double bond over onto the oxygen to give that oxygen a negative charge, right? And since this is an intramolecular reaction, we're going to form a ring, right? And I always start my numbering system from the attacking atom to the atom being attacked. So we're going to form a 1, 2, 3, 4, 5, 6-membered ring here, right? So I'm going to draw that 6-membered ring template out like this, where one of my atoms in the 6-membered ring is an oxygen atom. So that's going to be like that right there. So that's this 1, 2, 3, 4, 5, 6-membered ring, right? Where this is the new bond between atom 1 and 6 from the attack, right? Now we just attach the decorations onto the ring. At carbon 3 or atom 3, we have an ethyl group. At atom 6, we have an isopropyl group and an O minus group, right? But that O minus group will get protonated somewhere in the mechanism to become OH, right? And can someone tell me what this functional group is right here when we have carbon bonded to one OH group and one OR group, right? One half of the groups is an OH group, the other half is an OR group. What would this functional group be here?
Hemiacetal.
Yep, hemiacetal, right? Hemiacetal. Does anyone have the key to this? I want to make sure we have that right. Let's see. V, D, F, G, H, I, J, K, L, V. Right here. This hemiacetal right here, which is what we got. Okay. Now let's move on to F. F right here. Okay. So whenever you see PTSOH, think of that as acidic conditions, right? Think of it as like H2SO4. And if we're in acidic conditions, this carbonyl oxygen here is going to be protonated. That's the most acidic oxygen right there. And when this carbonyl oxygen gets protonated, we are activating this electrophile. We're converting that weak electrophile into a strong electrophile, whereas this weak nucleophile here, the alcohol, can then attack that electrophile and push the double bond over onto the oxygen. So this is another intramolecular reaction, right? Where the nucleophile is on the same molecule as the electrophile, forming a 1, 2, 3, 4, 5-membered ring this time. So if I draw this 5-membered ring out template like this, where one of the atoms in the 5-membered ring is this oxygen right here. And let's say this is 1, 2, 3, 4, 5. And if we connect the decorations, carbon 2 has this propyl group right there, which is why I'm going to put a propyl group on carbon 2 right here. 1, 2, 3. At atom 5 right here, we have a hydrogen, which I'm going to leave as invisible, and now an OH, right? Which gives us another hemiacetal because this carbon here has one OH group, another OR group. But this is a cyclic hemiacetal, just like the other one. The other one was also a cyclic hemiacetal. V right here, cyclic hemiacetal. Let's double check the key for this. F. Um, it is, yep, that hemiacetal right there, cyclic hemiacetal with the propyl group right there. 1, 2, 3. Okay, next one. Let's do AM. AM. Okay, let me go get more space for this one. Okay, so for this one right here, this is midterm 2 material with the benzene reactions. We see that we have a benzene ring in our starting material reactant with 2 groups. And these 2 groups are EDGs, right? This is an EDG. This is another EDG. If we have 2 EDGs, we have to choose the stronger EDG over the weaker EDG, right? This R group here only donates electrons by induction, making it a weak EDG. This EDG here is donate electrons by resonance, making it a strong EDG. So this right here would be our directing group. And we said EDGs are ortho para directors because of the resonance. So the group would be attached to the ortho position here, but not the para position in this specific example, because the para position is already blocked off by the alpha group here. So we see in the first reaction and second reaction, they go together. We're going to do a Friedel-Crafts acylation reaction, right? So the first 2 reactions are going to put that acyl group on the ortho position like this. Okay, the EDG is still there. This ethyl group is still here. Now, the next step right here with the acid, water, and heat is going to hydrolyze this ester into an alcohol, right? But that's a 118C mechanism. So I don't know why this is on this practice worksheet. And I could see her putting a geminodiol here as well, but that's very unstable. So I would say the carbonyl is the more major form. So I'm just gonna keep the carbonyl there. Right? So I'm gonna say this is my final answer, but let me double check that really quick. AM. AM. Yeah, right. This right here, maintain the carbonyl. We don't go to the geminodiol because the geminodiol is unstable. We want to maintain the carbonyl group so it stays as a carbonyl. This one right here, I don't know why that was on this practice worksheet. Converting an ester into an alcohol is a 118C reaction. That's a hydrolysis reaction. Hydrolysis of a carboxylic acid derivative, like an ester, for example, derivative back into the carboxylic acid and the leaving group. In this case, the leaving group is the alcohol. Right. So whenever you see this, ester here with acid, water, and heat, that's gonna get hydrolyzed into alcohol. Right. Where the alcohol oxygen, I'm gonna highlight in red here, is this ester oxygen right there. Right. Don't worry about the mechanism. That's gonna be the very beginning of 118C. Okay, let's move on to the next one. It's gonna be AW. AW. Right here. Okay. So for this AW right here, we have a carbonyl, aldehyde specifically, and an organometallic, an organolithium to be specific, right? Which I'm gonna draw that out in bond line form, CH32, CH2Li, where this, think of it as like a Grignard reagent. Whatever is attached to the MGBR or the Li is negatively charged, is our nucleophile, my star atom. That is a strong, strong nucleophile, right? We have an aldehyde here where the carbonyl carbon is partial positive charge, making that the dot, the electrophile. The star is going to attack the dot, popping the double bond onto the oxygen, giving us this intermediate here. So when I draw this out, I'm going to draw the O minus going up like that. This is the dot carbon right here. This is the star carbon right there. And this is the new bond that gets formed between them after the reaction, right? And the lithium just dissolves away in the solution, where we see the star atom is attached to this isopropyl group, which I'm going to draw the isopropyl group out like that. The second step, H3O plus, is gonna protonate the O minus to become neutral alcohol. PCC is an oxidizing agent, which would oxidize the secondary alcohol to a ketone, a carbonyl. And now this is the new material here, where we have NH2, NH2, NaOH, water and heat. That is going to make an imine, right? Because an imine formation is going to come from either ammonia or some primary amine, NH2. The tricky step here is this primary amine, right? This primary amine, the R group, you could think of that as another NH2 group, right? Because it's NH2, NH2. So when we react this ketone or carbonyl with this amine right here, we're gonna replace the oxygen with the nitrogen, where the R group of that nitrogen is going to be another NH2 group, right? You could think of this as the R group, like an ethyl group or something, which is going to be the R group of the primary amine, which is this R group right here. Let me actually make sure this is right though. Let's see, AW. AW. NaOH. Okay. I know what's going on here. When you see these reagents right here, we're not doing imine formation. What reaction do you think of when you see this set of reagents? Right? What reaction do you think of when you see those set of reagents? It's not gonna be imine formation. What I did was wrong. Starts with a W. The reaction name starts with a W. Right? And it has like an animal to it. Vidig. So Vidig reaction is going to involve a carbonyl and an ylide, right? The double bond, carbon double bond phosphorus triphenyl. We don't have any carbon double bond phosphorus triphenyl here. This right here is going to be, when you have these reagents, is going to be Wolff-Kishner. Wolff-Kishner reduction. Right? And whenever you see these reagents and you think of Wolff-Kishner reduction, the easier way to predict the product is that the carbonyl will go away, right? You just get rid of the carbonyl completely. Okay. And this would be your final answer here. Okay. It won't be imine formation. The biggest signal here is the basic conditions, heat and NH2, NH2, because Wolff-Kishner reductions are going to be in basic conditions, which can interfere with other things if they are base sensitive, which means that they can react with the base, like an acid, like carbonyl, which will get reduced down all the way to an alkane, but any other group like an ester or carboxylic acid, they could be affected by this reaction as well. Like think of some other acid, right? This Wolff-Kishner reduction would just completely get rid of the carbonyl there. Next one, BP. Okay, BP. BP is gonna be right here. Okay. So this one right here is gonna have one of the chapter 18 reactions with the enone or alpha beta unsaturated carbonyl. Whenever you have this tethered thiol here with zinc chloride, you are going to make this thiol acetal protecting group, right? It's like the acetal, but with sulfur atoms, like this on a carbonyl. And then when that reacts with H2 Raney nickel, the H2 Raney nickel is a reducing agent that will completely get rid of that protecting group to turn it into an alkane, like that. Right. And H2 radiant nickel, I don't know if it would reduce the alkene as well to the alkane, but I'll just guess that it also does reduce the alkene down to alkane. And we'll check the key here. We'll check what the key is here. BP. Because it's H2, I think of H2 PDC, H2 radiant nickel. BP. Yep. So H2 radiant nickel would do two things. H2 radiant nickel would get rid of this thioacetal protecting group and the alkene right there. It reduces both things. Reduces the thioacetal, that goes away, and reduces the alkene, that goes away. Right. But let's say now that you want to just get rid of the thioacetal, right? Let's say we have this structure with the alkene still intact and the thioacetal still intact. If you use this chemical soup instead, HgCl2, CaCO3, CH3, Cn, and water, that's going to convert the thioacetal back into the carbonyl. It would deprotect the thioacetal back into the carbonyl. The alkene will maintain and stay intact. That goes back like that. Okay. So now let's go over the chapter 18 reactions. Let's see, how do we do this? Let's see. Okay. I think, what would you guys prefer to do? Focus on the chapter 18 reactions or the problem set problems and the practice final problems?
Can you go over problem set number 11?
Problem set number 11. Okay. Yeah, let's do problem set number 11 and then do some practice final problems. Let me see. Links. Can you send me the problem number 11? I don't have the problem set with me.
Okay, I'll text you.
Thank you. Yeah, I don't have the keys, so we'll just work through it together. Okay. Yeah. Oh yeah, and then some people requested to do the spectroscopy problem on the practice final as well. Has she posted the key yet for the practice final? If not, we could just try it and then see if it makes sense or not. But if she did, then I haven't looked at it yet. I'll show you guys what my thought process is on the spectroscopy problem, and then see if I could get it right.
I sent it.
Oh yeah, I see it. Okay. So this problem here is having an alpha beta unsaturated carbonyl or an enone reacting with CH3, CH2, CH2M. Second step, acid workup, H3O plus. Look at the given substances. Fill in the blanks with the single letter code of the appropriate substance or the appropriate descriptive vocabulary word phrase to complete the description. Computer, if the metal is RLI, the major product for the reaction is compound. Okay, so they're saying if M is Li, we would get this here, CH3, CH2, CH2, Li. This would be our nucleophile. Okay, this is perfect because this problem here would lead me into teaching the other chapter 18 reactions that are not Aldol, Michael, and Robinson, right? So an alpha, beta, unsaturated carbonyl, aka an enone, looks something like this. Right? Where this is our carbonyl right here, the carbon double bond oxygen. This is our carbon neocarbon, not the alpha carbon, right? That first carbon right there is the carbonyl carbon. The carbon away is the alpha carbon. This is the beta carbon, right? If you have another carbon coming out like that, this is still technically the alpha carbon, but we're not interested in the alpha carbon. We're interested in the alpha carbon that is double bonded, right? So when we talk about the alpha carbon here, we're talking about the alpha carbon that has the double bond. Okay. This is the beta carbon because it's 2 carbons away from the carbonyl. We see that because there's a double bond between the alpha and beta carbon, or an unsaturation between them, we call this an alpha beta unsaturated, because there's an unsaturation between the alpha and beta carbonyl, right? Because it's alpha and beta to a carbonyl. You could also see this as an enone, where it's like an alkene next to a ketone, right? But it does not have to be a ketone. It could be an aldehyde. So that's an enone. Now, whenever you see an enone, right, always think of an electrophile. An enone is always going to be an electrophile of some sort of reaction, like microaddition, Robinson annihilation reaction, and all these other reactions I'm going to go over with you. Right? So there are going to be 2 possible electrophilic atoms in this enone right here. Let me actually draw this out without the other labels. We know that the carbonyl carbon here is partial positive because it's attached to an electronegative oxygen atom, like that, right? But this overall enone here, or alpha beta unsaturated carbonyl, that carbonyl carbon is not the strongest electrophile, right? The strongest electrophile is actually going to be the beta carbon here, which will have a bigger partial positive charge, making that the better electrophile. The reason why is because when we do resonance, right? Go back to resonance and get the other major resonance structure by pushing the double bond over to make a double bond there, popping this double bond onto the oxygen, getting this resonance structure here. We see that the beta carbon here has a full positive charge, right? This was the alpha carbon, this is the beta carbon, this is the alpha carbon, this is the beta carbon. We see that in the resonance structure, this beta carbon here has a full-on positive charge, making that the better electrophile, a bigger positive charge than the carbonyl carbon, right? Because if we look at the carbonyl carbon for both resonance structures, there's no full positive charge on the carbonyl carbon at all. Whereas if we look at the resonance structure, there is a full positive charge on the beta carbon, making that the better electrophile. The alpha carbon is not the electrophile at all. So whenever you see an enone, never react with the alpha carbon. You're either going to attack the beta carbon or the carbonyl carbon, right? And to tell which one you attack, you look at what kind of nucleophile you have. If you have a soft nucleophile, you're going to attack the beta carbon. And I'll show you what the soft and hard nucleophiles are after this. But when you have a hard nucleophile, you're going to attack the carbonyl carbon, right? So there's less hard nucleophiles than soft nucleophiles. Soft nucleophiles are like every nucleophile that you know of. The hard nucleophiles, there's only like 2 that I want you guys to know, right? So let's make a list of the hard and soft nucleophiles. So just memorize what the hard nucleophiles are, and then everything else will be soft nucleophiles. So the hard nucleophiles will be in the form of a hydride minus or an R minus. And H minus are going to be in the form of lithium aluminum hydride or sodium borohydride. Those reducing agents. Whenever you see any reducing agent, always reduce the carbonyl, right? Always reduce the carbonyl to an alcohol. The form of R minus is going to be RMGBr, a Grignard reagent, or RLI, organolithium reagent, organometallic reagent. Any organometallic reagent is a hard nucleophile. That's gonna attack the carbon as well. Everything else are soft nucleophiles. So the common ones for this chapter is going to be an enolate ion, right? So let's say we have this enolate ion right here. But here's a trick. What atom here is actually the nucleophile, right? Based on this structure that I just drew. What atom is a nucleophile in this enolate ion? Would it be the O minus? Would it be this carbon, or would it be the alpha carbon? That's the nucleophile. And here's a hint. Think about resonance here. Right. So when we do, yeah, it's going to be alpha, because when we do resonance, we're going to get this resonance structure where there's going to be a negative charge on the alpha carbon, right? And if we look at the stability of the negative charge here, the negative charge is less stable on the alpha carbon, making it more reactive, more nucleophilic. The negative charge on the oxygen is more stable, making it less nucleophilic, less reactive. So whenever you see some sort of enolate ion, the nucleophile is going to be that alpha carbon, right? Not this O minus. The O minus will not attack an electrophile. It's the alpha carbon that will, by reforming that carbonyl and having that star attack an electrophile. Another one that you might see is an alkyne anion. You might see an enamine as one, but the nitrogen here is not the nucleophile, it's the alpha carbon because of the same reasoning. Another one you might see are everything else, NaCN, Na, N3. It could even be NaOCH2, CH3. It could also be a neutral amine, RNH2, right? Because this neutral amine here is a strong nucleophile, right? All of these nucleophiles here are considered strong nucleophiles when we did SN2, SN1, E1, E2, but they're going to be considered soft nucleophiles when we react with an enone, right? So all of these soft nucleophiles here will attack the beta carbon of the enone. When you have a hard nucleophile, like a reducing agent or an organometallic, that's going to attack the carbonyl carbon of the enone. Okay, let's go back to that problem set and use what we just learned. So this is an organolithium reagent, an organometallic reagent, which is a type of hard nucleophile. This is our enone here, our alpha beta unsaturated carbonyl. So we talked about two possible electrophiles, the carbonyl carbon or the beta carbon. Since we have a hard nucleophile, that hard nucleophile will attack the carbonyl carbon, right? So our electrophile here is going to be this carbonyl carbon. That's not always the case though, right? Because if you have some other reagent like in enolate ion or alkynyl anion or an amine, it's gonna attack the beta carbon instead of the carbonyl carbon, pushing everything over like that, right? But because we have a hard nucleophile in this problem, we're gonna attack the carbonyl carbon and pop the double bond onto oxygen like that to give us this intermediate here. O minus, new bond between star and dot. The dot is attached to ethyl group. Boom, boom. Lithium goes away. Alkene still here. Methyl still there. Second step, acid workup. Protonate the O minus into OH, neutral alcohol. Boom, boom, boom. Okay, let's see what the question was asking. the major product for the reaction is compound C. Wait, let me make sure there's no clickbait going on here. Yep. It's not H because we need the double bond there. It's not that, it's not that, it's not that. It's not M. We don't have an ether. We don't have that. Okay. So the first one is gonna be C. This is an example of a, oh yeah, I forgot to say. When the hard nucleophile attacks a carbonyl carbon, there's two ways that you could call that. You could call that a 1-2 addition or a direct addition, right? And the numbering system is going to go something like this. Our oxygen atom is number 1, carbonyl carbon is number 2, alpha carbon is number 3, beta carbon is number 4. When you have a soft nucleophile attacking the beta carbon, that's going to be called a 1-4 addition because it attacked the fourth atom of this enone, or a conjugate addition. Conjugate addition. So these are just like names of what's happening here. So on the problem set, I would probably put direct addition unless Levens specifically said 1-2 addition, or she puts both and she accepts both. Yeah, I would put direct addition or 1-2 addition. I would make sure with her lecturer. Okay, next one. If the metal is Gilman reagent, R2 copper lithium, the major product. Okay, yeah, so the other reagent for this new chapter 18, is going to be the Gilman reagent, right? Which is a type of soft nucleophile. And that's going to be R2 copper lithium. Think of this as a weak organometallic reagent, weak Grignard reagent, weak organolithium reagent. Right, and because it's so weak, we need at least 2 R groups on the reagent that would add the R group once, right? But you need 2 R groups. So if the metal is R2CuLi, the major product for the reaction is initially, which immediately converts to a compound via a mechanism. The overall process is an example of a conjugate addition. Okay. So if we have this molecule here, the enone, reacting with CH3, CH2, CH3, CH2, to copper lithium. This is a soft nucleophile, right? This Gilman reagent here. And we said soft nucleophiles will attack the beta carbon, right? So we're going to attack the beta carbon, shift the double bond over, and pop that double bond onto the oxygen like that to give us this intermediate here. O minus, new bond between star and dot. The star here is attached to an ethyl group. 1, 2. Right? The acid workup step, when the acid comes in, H3O plus, be careful here. Do not proton the O minus, right? Because this O minus here is next to an alkene. So this whole thing right here that I'm boxing is the enolate ion, right? Where that enolate ion, the more basic or nucleophilic thing is this alpha carbon here. So the alpha carbon is going to get protonated, right? So to do that, we have to reform that carbonyl and have this alpha carbon grab the hydrogen and kick out the water molecule to get this final answer here. 1, 2, 3, right? So for Levin's problem set, I see what she's trying to say here. She does protonate the O minus first, but you'll still get to the carbonyl, right? So what she does is she protonates the O minus to get to this intermediate. And can someone tell me what you guys see here, what this is, based on chapter midterm 1 reactions? An alkene next to an alcohol is an ene something, not enamine, uh
Eno.
eno. Yeah, eno. Yep, eno. And then when you have an eno, do you guys know what it transforms into? Yes, it does tautomerization. Tautomerization into a carbonyl, right? Just like that. Okay. So the reaction is in the major product is initially compound F, right? Which immediately converts to compound. Where's Wado? E via a tautomerization mechanism. The overall process is an example of a conjugate addition or 1,4 addition. 1,4 addition or conjugate addition. I think she would accept both ways. Conjugate addition, 1,4 addition. So you would have to put 1 comma 4. Or you write the word conjugate addition because we had a soft nucleophile. If we quench the cuprate addition with CH3CH2I instead of H2O plus, the major product is now compound. Okay, so now they're changing up the second reactant. Right. The reactant here stays the same. The first step here stays the same. We have this organocuprate still. But now the second step is CH3CH2 Li. Wait, no, iodine. Hello, alkane. Right. So the first thing happens the same. The soft nucleophile attacks the beta carbon, pop that up there, shift that up there to get this intermediate here. Right? New bond between star and dot. Now, the second step is not an acid anymore. It's a halaalkane. So think of it the same way. This is an enolate ion right here. The more nucleophilic or the more basic atom is not the O minus. It's the alpha carbon. Because when we do resonance, the negative charge on the alpha carbon is less stable. And because it's less stable, it's more reactive, more nucleophilic or more basic. So what we have to do here is reform that carbonyl, the carbon double bond oxygen, and then have that alpha carbon attack this electrophilic carbon and kick out the iodine. SN2 reaction, SN2 mechanism, right? And that's going to give us this final product here. Where if I make this my star, this is my dot, that's the new bond between the star and dot. The dot is attached to a methyl group like that, and then this stays the same, which is compound O, compound O. Compound O. Okay. If the material is RMGBr, the major products for the reaction are a mixture of compounds. Okay. There's a mixture here. Why is there a mixture? Okay, she's saying that there is a difference between RLI and RMGBR then. So if she's saying there's a difference between them, which is I'm guessing that if you have an RMGBR, it could attack both the carbonyl carbon and the beta carbon, right? So the hard nucleophile for Levin's class, according to her, is gonna be an RLI, just an RLI. The RMGBR would not be considered a hard nucleophile. That would only attack the carbonyl carbon. According to Levin's, I think she wants to have the RMGBR attack both carbons, right? Because there's a mixture here. Because yeah, usually RLI and RMGBR are interchangeable, but for Leaves class, I have to check her lecture notes to see if she actually says this or not. But based on the problem set and what I'm seeing, there's two different products which can come from the two different attacks here. You could either attack the carbonyl carbon or the beta carbon, right? So let's try those out here. Okay. And then if you had CH3, CH2, MGBR, first step, second step, H2O plus. If this can attack both carbons, the carbonyl carbon and the beta carbon, uh, let's focus on the carbonyl carbon first. Attack that, push that up there, give us this O minus, 1, 2, 3, boom, boom, and then that O minus becomes OH after it gets protonated. So that's gonna be one of the products. If it attacks the beta carbon, shifting this over there, popping this up there, we're gonna get this intermediate instead right here. Star dot 1, 2, 3. Wait. 1, 2, 3. 1, 2, 3. Like that. O minus methyl. And then this O minus here does not get protonated, right? It's the alpha carbon. So we reform the carbonyl. What is alpha carbon will get protonated by the H3O plus. So now that is gonna reform the carbonyl here, right? Having a hydrogen here, which came from the H3O plus, which are compounds C and E. Has anyone tried this problem set yet? Is this what you guys got as well? Right, because I usually see RLI and RMGBR considered as the same thing, which is a hard nucleophile. But she's making them different here. She's saying that the RLI is the hard nucleophile and RMGBR is both a hard and soft nucleophile. It's a mix. Because she's saying it will give a mixture of compounds here. Right. She probably might. Wait, did she go over this in lecture yet? The conjugate edition, direct edition, 1,2 edition, 1,4 edition with the hard soft nucleophile, um, enone, alpha beta unsaturated carbonyl. Did she go over this in lecture yet?
Not yet, I think.
Not yet. Oh shoot. Okay. Yeah. But my guess right now is that it would be both C and E, where a Grignard reagent, RMGBR here, is considered a mix of a hard and soft nucleophile. Right. So what should we call it? We should call it what's the middleman, the in-between guy? Uh medium nucleophile. For Leibniz class is RMGBR, which can attack the carbonyl carbon and the beta carbon of the enone. The hard nucleophile attacks carbonyl carbon, soft nucleophile attacks beta carbon. Medium nucleophile attacks both carbonyl and beta carbon, giving you a mixture of products, right? Which is MGBR, RMGBR. Yeah, I think she is behind. What did she end on today? If you guys want to lecture today, this morning. Okay. For the last 15 minutes, what do you guys want to go over? The spectroscopy problem to see how I approach it and see if I could get it correct for the practice final? Yeah, let's do it. Okay. Aldol condensation. She ended on aldol condensation. Did she go over the three types, like the self or homo aldol, the mixed or hetero aldol, and the intramolecular aldol? Oh, she didn't go over the three types yet. What about micro addition? Did she go over micro addition? Robinson annihilation? No, probably not because she didn't go over the intramolecular one yet, which is needed for Robinson. Oh shoot. You guys have like one more lecture tomorrow, which is half of it, and then the other half is review. What? Oh my God, that's crazy. Okay. Yeah, I don't know how she's gonna finish, like with all this 1.4 edition, 1.2 edition stuff and everything else, like alpha, uh, halogenation, acidic conditions, basic conditions. Uh, I think she's gonna have to skip some stuff. Okay, 30 point spectroscopy. The first step we do is calculate the degrees of unsaturation,
Brian,
DOU.
can you
Yeah.
go over number 9?
Oh, number 9? Yeah, yeah. Let's go over number 9 before that. Number 9, identification. Okay, circle the substance in each pair that is lower internal energy, which means higher stability. If something has lower energy, it will have higher stability, and vice versa. If something has higher energy, it will have lower stability. They're inversely related. So she's asking you to find the more stable thing here. Then briefly state the chemical principle that describes why that substance is more stable or lower in energy. Okay. So if we have something like this right here, this right here is talking about this reaction. The way it's drawn is so weird, but it's talking about this alkene reacting with Br2 and water. Do you guys remember the intermediate of this reaction? What kind of ring gets formed in this reaction? Bromonium ion, right? Where the mechanism is that when we have Br2, one of the alkenes is going to attack the bromine, kick out the other bromine. And then at the same time, as this bromine here is gaining electrons, gaining a negative charge, and this alkene is losing electrons, gaining a positive charge, the bromine is going to come back and attack the other side of the alkene at the same time, giving us this bromonium ion here. Wait, I'm not going to include stereochemistry, but we are going to get this bromonium ion here, Br plus, right? Now, there's 3 different scenarios of this reaction for the three different solvents that we can have: CCl4 versus water versus alcohol. If you have CCl4, the bromine minus will just attack. There's no competition of nucleophiles. But if you have water or alcohol, the water or alcohol will introduce competition in the nucleophile, right? Where the water or alcohol, there's a million of them in the solution, so they would win. They would beat the bromine minus ion. In this case, we have water. And do you guys remember where water prefers to attack in the bromonium ion? Does it prefer to attack the more subside or the less subside? More subside, right? And then the way you can think about this is SN1 reaction, right? Imagine that this is a good leaving group right here, which it is. Which side would give you your more stable positive charge? Which side would give you your more stable carbocation? Which is the more subside, right? So there's going to be a bigger partial positive charge residing in that carbon, living in that carbon, because it's more substituted, more hyperconjugation. Whereas there's going to be a smaller positive charge on the less subside because it's less stable there, right? So the water would tend to go towards the more subside and break open the bromonium ion like that. So if we look at this one right here, what would you guys say is more stable? The dashed lines here are representing an attack or a bond breaking. Would you say the water wants to attack this carbon or this carbon? The left or right intermediate? Which one transition state? Which one looks more stable? Which one looks more substituted? Left one, yep. because the left one here has more R groups, more hyperconjugation, right? So we're gonna choose this as the lower internal energy or more stable one because more positive charge character, or you could say more hyperconjugation. Did she release the key for the practice panel yet? I don't have the key. Oh, she
Yes,
did?
I sent it to you.
Okay. Oh yeah, let me see. Thank you. Thank you. Is it still sending on text message? Or did you post it to the drive?
I sent it on message.
Oh, the message. I see. Oh, I see. Oh, it's this one here. Thank you.
Welcome.
Uh-huh. Um, let me see. Let's see. Two. Huh? Where is this problem? What? The key number 9 is nomenclature. There's the key for this one is not here.
Wait, I think I want to send you the wrong one. Hold up.
Uh-huh. Oh, yeah, that was the midterm 2. That was midterm 2. Midterm 2 key.
Yeah, there. You sent it.
Yeah, let's see. Oh, I see it. I see it.
Sorry.
Okay. It's okay. It's okay. Number 9. Yeah. So the reason that she put is larger partial positive charge attracts, right? This bigger positive charge here on the more side attracts the partial negative oxygen, which is why we see this is lower energy, more stable. Same thing, right? Okay. What? Oh, yeah. This is a negative charge. This is a positive charge. So when you have a negative charge, think of a pair of electrons like that. Is this aromatic, anti-aromatic, or non-aromatic? Midterm 2. Uh, these conditions are all met. The 3 conditions are all met. They're all cyclic, they're all planar, and they're all conjugated, right? If all 3 conditions are met, how can you tell what's aromatic versus anti-aromatic?
Anti would be when you have an even pair of electrons, right?
Yep, even pair of electrons. That's right. Which in this case, how many pairs of electrons are doing resonance here? How many pair? 4, right? Which are 1, 2, 3, 4 even pair, making that anti-aromatic. This one is 3 pairs, odd pair, aromatic. And aromatic is more stable than non-aromatic, which is more stable than anti-aromatic. So anti is the least stable. Aromatic is the most stable. Aromaticity is the reason. Let's see what she put. Aromaticity. Let's see. She put aromatic. Okay, next one. Now we have a positive charge here and a positive charge here. Is NO2 an EDG or an EWG?
EWG.
EWG, that's right. And if it's an EWG, we know that there would be a meta director. And the reason why they are a meta director is because they are going to put positive charges on the ortho and para positions, right? So this could be a positive charge here, 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 positive charge here. So when we see these positive charges right here, we have to see which one is more stabilized by resonance, right? So Now, which positive charge do you think looks more stable? The positive charge that is right next to another positive charge, a like charge, or the positive charge that is further away than the like charge? Do like charges attract each other or repel each other?
Repel.
Yeah, they repel each other. So this one here is going to be very unstable because those two charges are on each other, right? They don't like each other. That's going to be less stable, more energy. Whereas the positive charges shape are they're still close to each other, but not as like close as these two are, right? So this would make this more stable, lower energy, right? Let's say like charge, less like charge repulsion. She put, oh yeah, more specific. NO2 is EWG and destabilizes the positive charge, destabilizes the carbocation with direct ortho-para interaction, right? Because we see they put positive charges on the ortho and para carbons relative to the EWG, right? We see positive charge on the ortho and para carbons, which makes the positive charge less stable here, right? Because of the like charge repulsion. Okay, this one, I think you guys know. This one, less steric hindrance. Right, because this is a trans alkene, this is a cis alkene. Trans is more stable than cis because of less steric hindrance. If you look at the R groups here, they're facing away from each other. If you look at the R groups here, they're facing towards each other, increasing steric hindrance. Right, yeah, less steric hindrance. Next one. Okay, this one right here, we have to look at which one is conjugated and which one is not conjugated. We see there's an sp3 roadblock here, so there's no conjugation there. There is a conjugation here because there's a network of at least 3 adjacent p orbitals, right? We have 4 in specific that can do resonance with each other. So more conjugation, which she put conjugated. Okay, next one. I said earlier that the carbonyl is more stable than the geminal diol. And the geminal diol is when we have 2 alcohols on the same carbon like that. And the reason why is because if we look at this carbon right here, it's attached to 2 electronegative atoms, making this carbon here very electrophilic, very positively charged, very unstable, right? But I don't know how to put that in words. Let's see what she put. Oh, shoot. Let's see. Electron EWG makes a strong electrophile. And she circled this one instead. Let's see what's going on here, which is lower in energy. Let's see, CCl3. CCl3 exception makes a strong electrophile. Okay, I see what's going on here. So the thing that you have to watch out for is this group right here, this CCl3, right? This CCl3 right here, if I draw that in bond line form, Cl, 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 the chlorine here is more electronegative than the carbon, right? And because the chlorine is more electronegative than the carbon, that makes this carbon here very positively charged, very electrophilic. And if this first atom attached to the system here is positively charged, this makes this whole thing an EWG, electron withdrawing group, right? Which would make this carbon to carbon positive charge because it wants to like gain electrons, so it's stealing the electrons from that carbon to carbon. And because this is very electrophilic right here, that allows for the formation of a geminal diol to form. And this is the exception when a geminal diol would be major over the carbonyl, right? And there are other exceptions as well. I have it in my notes. Let me show you guys the exceptions just in case it shows up again on the final. Exceptions.
Can you repeat that again, Brian? My internet cut off.
Yeah. So usually the carbonyl is gonna be major over the geminodiol, right? Like if we have this carbonyl versus this geminodiol here, the carbonyl would be more stable, right? But there are some exceptions when the geminodiol is more stable than the carbonyl. And here are the exceptions. Right, let me just get to my notes to get to those exceptions. So, 2, 4, 6, 7. Okay, let's see. 118b. So she did go over the exceptions. Make sure to know the exceptions when a geminodiol would be more stable than a carbonyl. Let's see. Geminodiol. Okay, so here are some exceptions. Exception A is when you have a formaldehyde. When you have a formaldehyde and you react this with water, the geminodiol would be major over the carbonyl. The second exception is when you have strong electron withdrawing groups, which is the one that she tested on this exam. So if you have CX3, where X could be chlorine, fluorine, or bromine, any halogen attached to the carbonyl here, react that with water, that's when the geminodiol is more stable than the carbonyl. The last exception that you need to know about for this concept is strained ring. Right? So if you have a ring like that with a ketone and you react that with water, this would favor the geminodiol over the carbonyl. The reason why is because when we have this strained ring right here, it's locked into the 60-degree bond angle, right? Where we know that this atom here is sp2 hybridized, making it 120 degrees. Whereas this carbon here is sp3 hybridized, making the angle 109.5 degree, right? The difference between 120 and 160 is greater than the difference between 109.5 and 60, right? So there's more ring strain in the carbonyl form. There's less ring strain in the geminodiol form, right? So we want to relieve the ring strain by getting into this sp3 carbon, which is why the geminodiol is favored over the carbonyl. The reason why a strong EWG favors the geminodiol over the carbonyl is because this strong EWG here makes this carbonyl-carbon a strong electrophile, which will just react right away to get to the geminodiol. And then the reason why a formaldehyde would make the geminodiol favored over the carbonyl is because these hydrogens here are not EDGs, not EWGs, so they don't affect anything, right? And what else? Yeah. Yeah. So know these three exceptions when the geminal diol is going to be more stable than a carbonyl, right? Which showed up in this problem here, right? She was comparing this carbonyl with a strong EDG, the Cl3, versus this geminal diol with the same electron withdrawing group. And that's one of the exceptions where we have the geminal diol major or more stable over the carbonyl, right? And the reason is because the EWG makes the carbonyl a strong EWG, makes carbonyl strong electrophile. Okay, next one. So this one right here is going to talk about the inductive effect of the R group. We know that this R group here donates electrons inductively, like that, just naturally. The H atom here is not an EDG, not EWG. It doesn't do anything, right? And we know this is an enolate ion right here, which can do resonance like that, right? And because the negative charge here is trying to get into a negative charge system, that makes it less stable. And I'm going to say that this is more stable because there's no negative charges interacting with each other, right? Whereas the left structure has this negative charge, like EDG, reacting with a negative charge enolate ion system. And like charges repel each other, right? So let's see what the answer is and what the reason was. Yep. Less electron donation, less electron repulsion. And you could say better acid as well, but that's gonna talk about another factor. Right. And that's gonna talk about like if you have this carbonyl versus this carbonyl, and you compare acid A with acid B. Acid B is a stronger acid because it gives it more stable conjugate base. If I draw the conjugate base out like this for both, the conjugate base for the aldehyde is more stable because there's more resonance that's able to happen there, right? Whereas if I draw the resonance here, that's still the same amount of resonance, but this R group here that's donating electrons into the system is making it less stable, right? Because it's introducing like charges to each other, making the system less stable. Whereas the hydrogen is not interfering with anything at all because the hydrogen is on EDG, it's on EWG, making this unaffected, right? More stable. Yeah, and you'll learn more about that in 118C. Like the beginning of 118C will go more into this topic here. But for this chapter, think about less electron donation, less electron repulsion, right? We don't want electrons to be near each other, like that. Any questions on this question, this part? Yeah, so too much electrons, right? This EDG here is giving more electrons into the negative charge system, which is bad. We don't want negative charges and negative charges together. That's electron repulsion. Like charges repel each other. Whereas this hydrogen here is just sitting there, just chilling there, right? It's not donating electrons, it's not withdrawing electrons, it's just chilling there. But if you have something like this, where you have the same enolate ion, but now you have an EWG, like NO2, where we know that the N has a positive charge and one oxygen has a negative charge. This EWG here would make it more stable, right? Because opposite charges attract. They stabilize each other. So if you were comparing that and that, this would be more stable. The group with the EWG, because the EWG stabilizes the negative charge. Opposite charges attract. But if you're comparing electron repulsion with nothing, nothing wins, right? It's more stable than the repulsion. Right. Okay. Now let's finish off the session by the spectroscopy problem. Okay. 2 times 15 plus 2 minus 20 all over 2. That's going to be 30 plus 2 minus 20 all over 2. 32 plus 20. No, 32 minus 20. That's 12. 12 divided by 2 is 6. 6 DOU. Right? And if we have 6 DOU, I'm going to assume that we have a benzene ring. And in this case, I know that we do because the 6 to 8 region on the HNMR is the benzene region, right? And because at the benzene region, I see 4 hydrogens in total, 4 benzene hydrogens in total. I know that we have 2 R groups, 2 substituents on the benzene ring, and it's either going to be ortho, meta, or para. And I went over the pattern of ortho, meta, or para, like some video review session ago, right? Where I'm gonna briefly go over that here. Ortho, meta, para. If your 2 substituents are ortho to each other, they look like that. If your 2 substituents are meta to each other, they look like this. If your 2 substituents are para to each other, they look like that, right? And now I'm gonna draw in the unique hydrogens for each. So all of these 4 hydrogens are unique to each other. All of these 4 hydrogens are unique to each other. They're different. But at the para, there's a set of hydrogens that are the same and another set that are the same because of the plane of symmetry, right? So we know that the benzene is between 6 to 8, 6 to 8 on the HNMR, 6 to 8. The red hydrogen has 1 neighbor, so it should show up as a doublet. The pink should show up as a triplet because it has 2 neighbors. The purple should show up as a triplet because it has 2 neighbors. The green should show up as a doublet because it has 1 neighbor. The pink should have a doublet. The red should have a singlet because it has no neighbors. The purple should have a triplet because it has 2 neighbors. The green should have a doublet because it has 1 neighbor. Now, we have the red, which has 1 neighbor, a doublet, pink, 1 neighbor, a doublet. If we draw in the right in the integration, there's 1 H there, 1 H there, 1 H there, 1 H there, 1 H here, 1 H here, 1 H here, 1 H here. But for the para, we have 2 red H's and 2 pink H's, right? So these are the patterns that you have to see to tell whether you have an ortho benzene ring, a meta benzene ring, or a para benzene ring, right? The biggest signal here is the 4 benzene hydrogens between 6 to 8, right? They all add up to 4, add up to 4, all add up to 4, meaning that you have 2 substituents, either ortho, meta, or para to each other. And then you tell that by looking at these patterns. In the HNMR here, we have 2 doublets that have 2 hydrogens, which means that we have a para benzene ring, right? But I don't know what the 2 groups are yet. I'm just gonna put a squiggly line like that and a squiggly line like this for partial credit for now, right? Now, the next thing I would look at is the IR, right? So this IR here is gonna be 3100 sp2 carbon hydrogen, the alkene hydrogen. I'm gonna ignore that. That's the regular sp3 carbon hydrogen. This is the carbonyl, carbon double oxygen, around 1700. This is the carbon double bond carbon, the alkene. And then I'm gonna ignore everything else. Okay. So we do have 2 oxygens here. So 4 DOU comes from the benzene ring. We do have a carbonyl. That's 5 DOU. I'm trying to figure out what the other DOU would be because we have 6 DOU. Okay, let's see. Let's see. And I'm gonna guess that the 6 DOU here is another alkene, right? Because we have 2 1600 peaks, 1640 and 1635. So we're gonna have 2 alkenes, and then I knew that because I saw we have peaks between 4 to 6, and we have J values, right? So now my 6 DOU are gonna come from this 1 carbonyl, 4 from the benzene, so that's 5, and another from an alkene, a carbon double bond carbon, right? Where we have J values here, where we know that hydrogen A and hydrogen B are going to be trans to each other because they have matching J values of 16. So if I make this my hydrogen A, this has to be hydrogen B because I know that they are trans to each other from the J values. They match 16. Hydrogen C and hydrogen A match with 10, right? Which means that they're going to be cis to each other. If I drew hydrogen B down here, I have to draw hydrogen C down there as well to make them cis to each other, right? And then this is going to be my other fragment right here, which is going to connect to the molecule somehow, right? But my alkene here is going to be looking like this in the molecule, like that. So draw that out for partial credit. Now let's try to connect the pieces here. Okay. Now, I'm gonna say that because we have two oxygens and one of the oxygens is a carbonyl, I'm gonna guess that we have an ester somehow, right? So I'm just gonna put an oxygen right there. And then the two hydrogens right next to the ester, I'm gonna highlight that pink to show these pink hydrogens right there. The reason why I made those these two pink hydrogens, is because they are in the electronegative region, 3 to 4, right? Right next to this oxygen right there. And we see that they have 1, 2, 3, 4 subpeaks, which means that they have 3 neighbors. And its 3 neighbors are going to be these 3 neighbors here that I am going to circle in black. Right, so that's the end of the chain. And we see that those 3 neighbors has those 3 hydrogens right here has 2 neighbors, which are going to represent these 3 hydrogens here with a triplet representing 2 neighbors, right? So I'm just going to cross out the peaks that I already used so I don't get distracted by the other peaks like that. So now we got these peaks to account for, right? So let's see how many carbons we used up so far. We used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons so far. But we got 15 carbons. So we got to use 4 more carbons. And now this part here is the trickiest part, right? Like the bunch of 2 H's in a row. Because this could be like a chain of CH2, 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 something like that, right? We know that 2 to 3 is going to be the alpha region, which means that it's going to be alpha to a benzene, alkene, carbonyl, or an alkyne, right? Or even the terminal alkyne hydrogen. So let's start with those. I'm going to say that one of the 2 hydrogens here are going to be alpha to this alkene right here. Right, let's get this out of the way. Okay. So if I say that this 2 hydrogens are going to be highlighted red, I'm going to make these 2 hydrogens here highlighted red. We see that they have 3 subpeaks, which means that they will have 2 neighbors. So I'm going to draw its 2 neighbors out like this. Right. We already see 1 neighbor. We got to introduce 1 more neighbor here somehow, but I don't see any peak with 1 hydrogen. Unless this does not count, but it should count though because it's a carbon. 1, 2, 3. And if we only want 1 hydrogen there, then we got to do something here. But if this is 1 hydrogen, there has to be a peak that has 1 hydrogen, but there's no peak with 1 hydrogen, so that can't be it. Let's try. Okay, so let's not make the thing there, right? I'm going to make the alpha hydrogens to the carbonyl then, okay? Because the alkene did not make sense. Let's put the 2 alpha hydrogens right here, which I'm gonna highlight in red, which are still this red highlighted peak right there with 2 neighbors. And now this does make sense because I could give its 2 neighbors right here, right? Because this carbonyl carbon here has no hydrogens, so there's no neighbors there. And I could say that this purple highlighted hydrogens is gonna be this purple one here with 1, 2, 3, 4, 5, 4 neighbors, which are gonna be these 4 neighbors here, right? And we also have another 2 hydrogens with another 4 neighbors, which I'm gonna say is this blue-headed hydrogen, which is this one, 1, 2, 3, 4, and then its other 2 hydrogen neighbors could be these ones here, right? Which could be the ones that are alpha to this benzene ring. So I'm gonna highlight that in gray, which is this gray right here, and this has to connect to the benzene ring in order for it to be alpha or allylic, right? And that means that I'm going to connect these together like that to get this final product here, final molecule here. 1, 2, 3, 4, it's a lot of CH2s. and then alkene like this. Wait, hold on. Um, what's this? HD? Where did HD come from? Okay, I'm just gonna ignore that. I don't know what what that is. Let's see here. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 carbons. That matches with the chemical formula. Do we have 20 hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 hydrogens, 2 oxygens, 6 DOU, 4 from the benzene, 1 from the alkene, 1 from the carbonyl. That's 6 total. We do have the alkene. We do have the benzene with the para substitution to it, and we do have the carbonyl and the 2 oxygens. Let me double check the key to see what it is. Go all the way down. Okay. This is what she put. Let's see the difference. So she had an ether and she had this enone instead. But let's see what's the difference here. The 2 hydrogens here of this alkene are these 2 hydrogens right here. And then the 1 hydrogen right here is this 1 hydrogen right here with no neighbors. Or it only 2 neighbors, right? Which are these only 2 neighbors here? Because this carbon here has no hydrogens, this carbon here has no hydrogens. We do have the CH2, CH3 that is next to an oxygen atom, which is that part right there. We do have 1, 2, 3, 4, 1, 2, 3, 4 CH2 chain coming out like that. So this and this got swapped, but I can't tell the difference between what they are on the NMR. Because the number of neighbors, they make sense for both of them. Everything else makes sense. So let's see. Let's say if structure given grade structure, if no structure grade labeled work. C2, C2. Let's see what she did. Conjugated terminal. Conjugated ketone. Why is it conjugated though? Like that. 2 alkenes, any ether, 2H. What's the difference? What does that mean? Yeah. Uh oh shoot. Let's see. Thank you. CNMR. Oh yeah, maybe to tell the difference, you have to look at CNMR. I see. Yeah, because what she put on the key is like something like this to get to that thing. But I don't know what this means, these symbols. Conj ketone, conjugated ketone. Fine. And she put something like this with the peak like that to get this. Is this CNMR? Or what is this thing representing? The CNMR tells us, oh, okay, yeah. Someone said CNMR tells us if it is an ester or just a carbonyl, right? And then on the CNMR, it would just say that it's just a carbonyl that's conjugated, no ester from the CNMR. But I did not use the CNMR as you guys saw. Like I never look at the CNMR, but that was needed in this case to get the exact specific structure. So I wouldn't get full credit here, but I would get most of the points here. Right. So if you guys know CNMR, then that's good. Use it to get the specific structure. I don't know how to read CNMR, so I didn't use it. Okay. Any questions on that? Uh-huh. No problem. Good luck studying for the final. And are you guys okay with me posting this on YouTube publicly? Or no? Yeah, no problem. Okay. Yeah, no problem. Okay. See you guys. Good luck. Mhm, mhm. Okay.
Dude, they're so cute. They're so adorable.
I know. Or hold on, hold on.